It is the summer of 213 BC. Roman ships approach the Greek city-state of Syracuse, which has allied itself with Rome's great enemy, Carthage. Suddenly, one of the Roman ships catches fire, bursting into flames and throwing the invaders into confusion. Surely, they are too far away from the enemy battlements to be attacked. Then, a flash of light catches their eyes. The defenders are using giant mirrors to reflect the sun's rays, burning the Roman vessels like ants in a magnifying glass. From his vantage point ashore, an old man watches on as his secret weapons wreak havoc on the invaders. His name? Archimedes, the greatest inventor of the ancient world. The man known to history as Archimedes was born in the city of Syracuse in Sicily during the early 3rd century BC, probably around 287 BC. At that time, Syracuse was the foremost city on the island and the greatest of the Greek cities of southern Italy, a region known as Magna Graecia, Great Greece. Such was the level of Greek colonization there since the 8th century BC. Thus, although born in Sicily, Archimedes was Greek and emerged from within a Greek cultural and intellectual milieu. While Archimedes is commonly recognized as one of the greatest scientists and inventors in history, very little is known definitively about his life. Brief accounts of his life and career are found in the writings of Greek and Roman authors from centuries after his lifetime, and these have been embellished over the centuries. For instance, while we know that Archimedes must have been born early in the 3rd century BC, the notion that he was born in the year 287 BC is based on a claim from the 12th century AD by the Byzantine historian John Tzetzes. He wrote that Archimedes was approximately 75 years old when he died in 212 BC. Still, while Tzetzes was writing a millennium and a half after Archimedes' time, he does cite Diodorus Siculus, a Greek historian from Sicily writing in the 1st century BC, as evidence for these details of the scientist's life. Furthermore, according to the Greek mathematician Eutocius of Ascalon, who lived at the turn of the 6th century AD, a biography of Archimedes was written by a friend named Heracles. While this has been lost in the centuries since, and parts of Diodorus's histories have only survived in fragmentary form, we can assume that writers like Tzetzes and Eutocius, who were writing many centuries after Archimedes' time, did have substantial source material from which they drew their information. Finally, and perhaps most importantly of all, there are several scientific treatises that Archimedes wrote himself that have survived to the present day. In these, he provided prefatory letters to fellow mathematicians, which included further details about his own life. In one of his treatises, The Sand Reckoner, Archimedes states that his father was an astronomer named Phidias, who calculated the difference in size between the sun and the moon, based on the fact that Phidias was also the name of the most famous sculptor in ancient Greece, who decorated the Parthenon and made the monumental statue of Athena Parthenos that stood inside the iconic temple on the Athenian Acropolis. Archimedes' modern-day translator, Reviel Netz, a specialist in ancient mathematics, suggests that the scientist's paternal grandfather was an artist who named his son in homage to the great sculptor. Netz goes further by suggesting that Archimedes' name, which may be interpreted as the mind of the principle, is a reference to the principle or order of the universe. The Greek philosopher Plato, who lived in the 4th century BC, believed that the universe was governed by rational mathematical principles. Perhaps Phidias was a follower of Plato and gave his son this name to reflect his belief in a rational and harmonious cosmic order. Apart from this, nothing is known about Archimedes' family and early life. His mother's name is unknown. There is no indication if he had any siblings or whether he himself was married and had any children. Instead, many of the ancient works which mention Archimedes pick up his story much later in his life, during the 2nd. His lifetime was a vibrant one from an intellectual and scientific point of view. Within Syracuse itself, the city had oscillated over time from being a dictatorship ruled by military strongmen to periods of democratic government. At the time of Archimedes' supposed birth in the early 280s BC, the city's long-reigning tyrant, Agathocles, had just died, and the city's politics were once again entering a period of flux. A tyrant in this ancient context was a cross between a king and a military dictator. Geopolitical developments in Sicily and the wider Western Mediterranean in the 4th and 3rd centuries BC would also be central to Archimedes' life story. By the time of his birth in the early 3rd century BC, Sicily was caught in the middle of the rivalry between Rome to the north and Carthage to the south. Carthage was a Phoenician colony that had been founded on the northeastern coast of what is now Tunisia by settlers from Tyre in the Levant back in the 9th century BC. It subsequently emerged as one of the great trading and naval powers of the Western Mediterranean, securing control over large parts of North Africa, southern Hispania, and the Balearic Islands in the 6th, 5th, and 4th centuries BC. It had also set its sights on conquering wealthy Sicily. The Carthaginians had succeeded in doing so to some extent, claiming the western half of the island in the 4th century BC. But Syracuse, particularly during the long reign of Agathocles, had offered strong resistance to the Carthaginians and remained the preeminent power in the west of the island. Meanwhile, further to the north, a newer power was emerging. The Roman Republic was a rustic backwater state of central Italy for much of the 5th and 4th centuries, while Syracuse and Carthage were great powers to the south. But the Romans were becoming an extremely aggressive military people, and in the century prior to Archimedes' birth, they had won a series of wars against their neighbors, bringing a wide range of city-states in Latium and Etruria under their aegide to southern Italy, who had previously been mercenaries serving the tyrant Agathocles. When Agathocles died, the Mamertines seized control of the city of Messana, using it as a base for piracy and raids on their neighbors. Hiero, in a clever and ruthless move, led his own mercenaries out to confront the Mamertines, but held back his Syracusan citizen soldiers. The mercenaries were slaughtered, effectively purging his army of a potentially rebellious element. After retraining his citizen army, Hiero decisively defeated the Mamertines in a pitched battle. He was then proclaimed King of Syracuse. This victory, however, alarmed both Carthage and Rome. The Mamertines, desperate, appealed to the Romans for help. Rome, initially hesitant to aid a group of brigands, saw an opportunity to prevent Carthage from gaining complete control of Sicily, which would bring Carthaginian power dangerously close to the Italian peninsula. This decision by Rome to intervene on behalf of the Mamertines set off a chain reaction. Hiero, seeing the Roman threat, allied himself with his former enemy, Carthage. This clash of alliances, Rome and the Mamertines against Carthage and Syracuse, escalated a local conflict into the First Punic War in 264 BC, a major turning point in the history of the Mediterranean and a conflict that would define much of Archimedes' later life. This section describes how a clever and ruthless Syracusan commander named Hiero rose to power. He dealt with a rebellious mercenary army by using them as a sacrificial front line in a battle against the Mamertines, a group of raiders. After the mercenaries were wiped out, he retrained his citizen soldiers and defeated the Mamertines decisively, earning him the title of king. Hiero's actions, however, had a wider impact. The defeated Mamertines appealed to the Romans for help, leading to Rome's intervention in Sicily. This sparked a major conflict known as the First Punic War, which pitted Rome against its great rival Carthage. Archimedes, who was believed to be a kinsman of King Hiero, would be a direct witness to this epic struggle for control of the Western Mediterranean. The text also briefly touches on Archimedes' early life, mentioning he may have studied in Alexandria, Egypt, which was a hub of Greek learning at the time. It's likely he was exposed to the works of Euclid and other great thinkers there, laying the foundation for his future genius. This section discusses Archimedes' intellectual and creative life, focusing on his time in Alexandria, Egypt. While there, he corresponded with prominent Greek mathematicians like Konon of Samos and Eratosthenes of Cyrene, the latter of whom famously calculated the Earth's circumference with remarkable accuracy. The text then highlights one of his most famous inventions, the Archimedes screw, a device for lifting water. Although similar devices may have existed before his time, the invention is often credited to him and was used for purposes ranging from draining mines in Spain to irrigating fields in the Nile Delta. Finally, the summary touches on Archimedes' personal philosophy. According to the ancient biographer Plutarch, Archimedes viewed practical inventions as ignoble and vulgar, considering only pure mathematics to be of true intellectual value. This passion was so intense that he would often become completely absorbed in his work, forgetting even to eat or bathe. This section describes the turbulent geopolitical context of Archimedes' life. He lived through the First Punic War, a massive conflict between Rome and Carthage for dominance of the Western Mediterranean, which was largely fought on and around his home island of Sicily. During the war, the ruler of Syracuse, King Hero, initially allied with Rome, a strategic move given Carthage's long-standing rivalry with the city. Rome's military campaigns successfully led to the capture of the Carthaginian stronghold of Acragas and the occupation of most of Sicily. Despite Rome's eventual victory in 241 BC, the war was a long and difficult one. Sicily became Rome's first province outside of Italy, though Syracuse maintained its independence under Hero as a Roman ally. The Carthaginians, though defeated, did not give up. They were forced to give up their territories to Rome, but immediately began rebuilding their power in Hispania, modern-day Spain, with the clear intention of seeking revenge against the Romans in a future war. This section highlights the importance of Archimedes' surviving scientific writings in understanding his life, especially given the lack of other reliable historical sources. The text explains that Archimedes spent most of his life in Syracuse, where he created highly advanced mathematical works that were likely understood by only a small number of people at the time. The text then details the remarkable journey of how these works were preserved. In the 6th century AD, his treatises were compiled in Constantinople, the capital of the Byzantine Empire, and transferred from fragile papyrus to more durable parchment. A key figure in this preservation was Eutychius of Ascalon, who wrote commentaries that were later included in a compilation by Isidore of Miletus. While Isidore's original compilation is lost, it led to the creation of at least 3 copies in the 9th and 10th centuries, ensuring Archimedes' groundbreaking work survived for future generations. The most complete of these copies was dedicated to a prominent mathematician named Leo the Geometer. This section details the fate of 2 of the 3 main Byzantine copies of Archimedes' work, known as Codex A and Codex B. Both were taken from Constantinople by Latin Crusaders in 1204 and ended up in a papal library in Italy. There, a scholar named William of Moerbeke translated them into Latin, making them accessible to a wider audience. Codex B, which contained a unique text called On Floating Bodies, was later lost. The third and most comprehensive copy, Codex C, dating to around 975 AD, is better known as the Archimedes palimpsest. After Constantinople was sacked, it was taken to the Holy Land. Because parchment was very expensive, the book was unbound, its original ink was scraped off, and the pages were reused to write a Christian prayer book in the 13th century, a process that created a palimpsest. In this process, the pages were cut and folded, resulting in the loss of about 1/3 of the original codex. This remarkable book, with Archimedes' work hidden beneath the new text, was not fully examined again until the 19th and early 20th centuries. This section chronicles the rediscovery and incredible journey of the Archimedes palimpsest, the prayer book written in 1229 by a priest named John Myronus, was found in a Jerusalem monastery collection in the 19th century. A Danish scholar, Johann Ludwig Heiberg, was the first to recognize it as a text by Archimedes in 1906. Using only a magnifying glass, he managed to decipher enough of the hidden text to discover a previously lost treatise called The Method. The palimpsest had a tumultuous 20th century, spending decades in a Parisian basement before being sold to an anonymous American buyer in 1998. It was then deposited at the Walters Art Museum in Baltimore, despite being in worse condition than when Heiberg saw it. Modern technology and conservation work have allowed contemporary scholars to read even more of the hidden text, further enriching our understanding of Archimedes' genius. The survival of these treatises is described as a colorful history, highlighting the immense effort and luck involved in preserving these ancient works. This section begins by noting that while Archimedes' writings are valuable, the most famous story about him is the Eureka moment. This tale, first recounted by the Roman architect Vitruvius, describes how King Hero of Syracuse asked Archimedes to determine if a craftsman had cheated him by using silver instead of pure gold in a new crown. Archimedes was stumped until he stepped into a bathtub and noticed that the water overflowed as he submerged his body. In this instant, he realized he could solve the king's problem by measuring the displacement of water. Overcome with excitement, he allegedly ran naked through the streets shouting, "Eureka!" Greek for, "I have found it." The text then explains how Archimedes used his discovery. He made two samples, one of pure gold and one of pure silver, with the same mass as the crown. He found that the crown displaced more water than the pure gold sample, proving that it was not made of pure gold. This simple but brilliant experiment not only solved the king's dilemma, but also demonstrated a fundamental principle of buoyancy and density. This section recounts the famous Eureka story and another notable quote attributed to Archimedes. The Eureka tale, told by the Roman architect Vitruvius, claims that a young Archimedes solved King Hiero's problem of a fake gold crown. He realized the principle of water displacement in a bathtub and in his excitement ran home naked shouting, "Eureka! I found it." The text notes that this anecdote is likely a misunderstanding of Archimedes' work on buoyancy. The second anecdote, from Plutarch, contains one of Archimedes' most famous quotes, "Give me a place to stand, and I can move the earth." Plutarch explains that Archimedes demonstrated this principle to King Hero by using a system of pulleys to effortlessly move a large, fully loaded ship. These stories, though possibly embellished, highlight Archimedes' genius for both abstract theoretical knowledge and practical engineering. This section explores another famous story about Archimedes, his boast that he could move the world. The text cites an ancient work called the De Sophisti, which claims that Archimedes used a winch to launch a massive ship called the Syracusia for King Hiero, a task that shipbuilders couldn't manage. This claim is directly linked to Archimedes' groundbreaking work on levers, detailed in his treatises on the equilibrium of planes. Following Euclid's method, he established foundational principles about balanced weights and fulcrums. From these principles, he derived the law of the lever, which states that a small force can lift a heavy weight if the lever arm is long enough. His famous quote, "Give me a place to stand, and I can move the earth," is a direct expression of his confidence in this mathematical principle. This section of the text delves into Archimedes' work on levers and his method for determining the center of gravity of various geometric shapes. His famous boast about moving the world is directly connected to his treatise on the equilibrium of planes, where he outlines the principles of the lever. This work demonstrates how a small force can move a large object if the lever arm is long enough, a principle he supposedly used to help King Hiero launch a massive ship. The text also explains his use of proof by contradiction to find the center of gravity of a triangle, a more challenging task than that of a parallelogram. Finally, the passage introduces another of his treatises, Quadrature of the Parabola, which was dedicated to his correspondent, Odysseus, and begins with a tribute to his deceased friend and fellow mathematician, Conon of Samos. This shows that Archimedes was not an isolated genius, but was part of a larger network of Greek scholars. This section explores two of Archimedes' key works, beginning with his treatise, Quadrature of the Parabola. The text explains that Archimedes was fascinated by the challenge of squaring the circle, finding the area of a circle using a square. While he didn't solve that problem, he used a similar approach to prove that the area of a parabola is 4:3, the area of a specific triangle bounded by it. The passage then introduces the method of mechanical theorems, a unique work in which Archimedes reveals his mechanical method. In this treatise, addressed to his friend and fellow scholar Eratosthenes, Archimedes explains how he first discovered his mathematical proofs by treating geometric shapes as physical objects on a balance. This mechanical intuition allowed him to solve complex problems before he formalized the findings with rigorous geometric proofs. This mechanical approach, which he felt was a useful tool for discovery, was a private method he shared only with a select few. This section focuses on Archimedes' advanced mathematical methods, particularly his work on curved shapes and the concept of infinity. His investigations led him to a deeper understanding of mechanics and gravity, foreshadowing discoveries made by Galileo and Newton 2 millennia later. In his treatise on the equilibrium of planes, he determined the center of gravity for a parabola. He then tackled the problem of infinity in his work, Measurement of a Circle. Since a circle has infinite sides, he couldn't measure its area precisely. Instead, he developed the method of exhaustion, where he approximated the circle's area by using polygons with an increasing number of sides. This allowed him to calculate a remarkably accurate approximation of PIP, which was between 3.142286 and 3.11484. This method of exhaustion was a revolutionary precursor to the development of modern calculus by Leibniz and Newton, demonstrating the immense intellectual leap Archimedes made in his time. This section focuses on what Archimedes considered his greatest accomplishment, the treatise on the sphere and cylinder. Addressed to his correspondent Dositheus, the work details his proofs that the surface area of a sphere is 4 times that of its greatest circle, and that its volume is 2/3 that of a cylinder that encloses it. The text highlights Archimedes' regret that his friend Conon of Samos was not alive to appreciate these findings. It also shows Archimedes' generosity and collaborative spirit as he provided solutions to mathematical problems Dositheus had sent to Conon. The section concludes with an introductory letter to his treatise on spirals, in which Archimedes apologizes for the delay, explaining he first wanted to share his results with other mathematicians. This reveals his commitment to peer review and the scholarly community of his day. This section provides insights into Archimedes' intellectual relationships and his groundbreaking work on buoyancy. The text reveals that his correspondent, Dositheus, was likely more of a popularizer than a mathematician, as Archimedes had to intentionally include 2 false proofs in his work to see if anyone would catch them. This suggests Archimedes' primary intellectual partner was his deceased friend, Conon of Samos, whose death he repeatedly lamented. The passage then introduces Archimedes' influential treatise on floating bodies. Building on his work with geometry and centers of gravity, Archimedes established the foundational principle that a column of water with an object submerged in it weighs the same as a column of water alone. This theory was the basis for his principles of buoyancy, showing his genius in connecting abstract mathematical concepts to the physical world. Serves as Archimedes' drawing board, the sand reckoner is primarily concerned with very large numbers and the concept of infinity. He tells King Gelon that some people assume that the number of grains of sand on Earth is infinite, since there is no way of expressing such a number. Archimedes aims to demonstrate that not only is the number of grains of sand on Earth not infinite, but the number of grains of sand in the universe is not infinite. To do so, he had to expand on the Greek numbering system. The largest number the Greeks had a word for was a myriad, or 10,000. Archimedes first suggested that there can be a number as large as 1,000,000, or a myriad myriads. This was only the first step. Archimedes then proposed calling the numbers 1 to 1,000,000 the first order, with 1,000,000 as the first unit of a second order of numbers, and so on until the 1,000,000th order. Using various assumptions about the size of the Earth, the Sun, the stars, and their relationship to the entire universe, as well as his expanded number system, Archimedes calculated that the number of grains of sand to fill the universe was 10 to the power of 63. Many of Archimedes' assumptions in coming to this figure are erroneous, such as his assumption that the circumference of the Earth is 3 million stadia. His friend Eratosthenes' figure of 252,000 stadia is much more accurate. Archimedes also assumed that the Sun is no more than 30 times the diameter of the Moon. This was closer to the 12 times that his father had proposed, but still far from the actual ratio of 400 times. Archimedes also referred to the astronomer Aristarchus, who proposed a heliocentric model of the universe in which the Earth orbits the Sun rather than the other way around. Although Archimedes, like virtually all other ancient scientists, was not convinced of this, he accepted Aristarchus' argument that the universe was much bigger than commonly believed. Using his assumptions, Archimedes calculated that the size of the universe was a sphere 2 light years in diameter, whereas modern astronomy has shown that the observable universe is 93 billion light-years in diameter and is still expanding. The accuracy of Archimedes' answer is not as important as the process by which he arrived at it. Indeed, Archimedes was seeking to calculate an upper bound for the size of the universe in order to show that it is possible to represent a large number, such as the number of grains of sand in the universe. Nevertheless, Archimedes' interest in the heavens was not purely theoretical. According to the Roman writer and statesman Cicero, Archimedes constructed 2 astronomical models that were taken to Rome following his death. The first of these was a hemisphere that represented the night sky, while the second was a model of the universe based on the description of the astronomer Eudoxus of Cnidus, who lived a century earlier and whose work he references in The Sand Reckoner. Archimedes may have described the process of building these models in On Sphere Making, a lost treatise referenced by the mathematician Pappus of Alexandria, who lived in the 4th century AD. The Sand Reckoner is generally regarded as the most approachable of Archimedes' treatises and reveals a playful side to his character. He is also known for coming up with mathematical puzzles for his fellow mathematicians. Such is the case with the Stomachion, a treatise that appears in the Archimedes palimpsest. Here, Archimedes divides a square into 14 straight-edged puzzle pieces and asks how many ways the pieces can be arranged to form a square. It has been calculated that there are 1,752 different solutions to the puzzle. The branch of mathematics involved in finding different solutions to the same problem is known as combinatorics and is used in computer science to determine the most efficient way of solving a particular problem. Archimedes is also associated with a remarkably complex problem known as the cattle problem. It takes the form of a Greek poem of 44 lines addressed to Eratosthenes of Cyrene, in which he is asked to work out the number of cattle in the herd of the sun, god Helios, based on a series of increasingly convoluted numerical relationships between cattle of various colors and patterns.